for joining us for this special presentation of the Reverend Joseph Carrier CSC Medal, presented today in honor of Mary Burke Ryan. This is the highest honor for scientific achievement awarded by the College of Science and the University of Notre Dame. I'm Steve Corselli, interim W.K. Warren Foundation Dean of the College of Science. I'm thrilled you're here for the fourth hosting of this event to recognize an internationally renowned scientist. Before introducing our distinguished scientist, I'd like to share a few words about the legacy of the Reverend Joseph Celestine Bastille Carrier, CSC, him as a person. Father Carrier took over as Notre Dame's second botany professor in 1868 and specialized in science and math. He was named the first director of Notre Dame's scientific department, which of course is now known as the College of Science. In honor of his legacy, the College of Science awards the Carrier Medal, which we present to scientists whose groundbreaking research has fundamentally advanced the understanding of our world. Their discoveries not only transform their fields, but also reshape how science is taught. Past recipients of this medal include Nobel laureates Michael Levitt, Nobel Prize in Chemistry 2013, Thomas Sudoff, medical doctor, 2013 Nobel Prize in Physiology or Medicine, and Donald Strickland, PhD, 2018 Nobel Prize in Physics, all of whom have profoundly influenced how we understand and teach science. It is now my pleasure to invite to the stage, or down here anyway, Dr. David Galvin, Chair of the Department of Mathematics, to introduce our recipient, Dr. James Maynard.
Thank you very much, Dean Corselli. Can everyone hear me? So, as you said, the past recipients of the Carrier Medal have been in physics, biology, and chemistry. So, as chair of the Department of Mathematics, it gives me great pleasure to say that this year is the turn of maths. I am very, very delighted to introduce the 2025 Carrier Medal recipient, Dr. James Maynard, Fellow of the Royal Society and Professor of Number Theory at the Mathematical Institute at the University of Oxford. Dr. Maynard's title suggests, he works in number theory, and at its heart this is the study of the properties of the ordinary counting numbers, 1, 2, 3, etc. This is one of the most venerable branches of mathematics. It's also one of the oldest. There are problems being actively worked on in number theory today that Euclid would perfectly understand 2,400 years ago. Now, for most of that past 2,400 years, number theory has been considered to be very much pure, very abstract area of mathematics. But actually, there have been extraordinary applications discovered just in the last 50 years in computer security, in cryptography, in digital communication protocols. So within number theory, Dr. Maynard specializes in the study of the prime numbers. These are the atoms or the building blocks of all numbers. And his impact on the field has been absolutely spectacular. So it is fair to say that in the last 15 years, he has exposed beautiful and startling truths about the prime numbers that even 20 years ago we would have thought to be completely beyond reach. And we'll see some of this in the presentation that he's going to give in a few minutes. His work has been recognized with awards from the London Mathematical Society, the European Mathematical Society, the American Mathematical Society, and the Breakthrough Foundation Board. In 2022, he was awarded by the International Mathematical Union a Fields Medal. The Fields Medal is the highest honor that can be awarded to someone in our subject. It is an award that is given to, at most, 4 people every 4 years. It honors a young mathematician, a mathematician under the age of 40, who has made an unsurpassed contribution to our mathematical understanding, but also who has outstanding promise. And I have to say that Dr. Maynard has not just sat down and rested after being awarded the Fields Medal. Just about an hour ago, he finished a beautiful colloquium in the Department of Mathematics where he told us about his very recent work. It's recent enough that the paper still hasn't appeared in the Annals of Mathematics, where he is tackling probably the single most important open problem in mathematics, the Riemann hypothesis. So it gives me great pleasure to welcome you here today. We are so thrilled to be honoring you. And with that, I will pass the baton back to Dean Corselli for the presentation of the Carrier Medal.
Thanks so much, David. So it is now my great honor and privilege to bestow the 2025 Reverend Carrier Medal onto Dr. James Maynard. And so now, Dr. Maynard will present his talk, The Magic of the Primes. And we invite you all, after his talk, he's going to be joined by Kate Biberdorf, Notre Dame's professor for the public understanding of science, for a fireside chat, perhaps minus the fire, but where he will answer some of your questions. I think it'll be an exciting and engaging evening. So without any further ado, thank you very much.
Okay, thanks so much for the introduction, and it's a huge honor for me to be awarded the Carrier Medal. I'm really excited to have it, and in my talk here, I'll try and to communicate to all of you who've been very generous with your time to come here today why I find mathematics and prime numbers in particular so fascinating, and why I feel that this is a really important subject for people to study, and why I really love the subject. So I want to talk about the magic of the primes and why I find prime numbers so compelling. And the fundamental reason that I think primes are so fascinating is that, on the one hand, primes are amongst the most basic objects that you can possibly think of. That the whole numbers are maybe the simplest mathematical objects, and as was alluded to earlier, prime numbers are somehow the atoms of arithmetic, or the building blocks of whole numbers, and this means that they have a really fundamental role in not just number theory, but in lots of applications within mathematics. But then the big tension with this fundamental status of primes is that they remain mysterious, and quite quickly, even when you're asking basic questions about primes and how they occur, you run into famous problems that mathematicians have been stuck up for thousands of years. And so it's this combination of being fundamental yet being mysterious at the same time that I find really compelling about primes. So first of all, why are primes building blocks? Well, there's a basic principle across the whole of science that scientists are lazy, and most things in our universe are just sort of too complicated to really think about all in one go. And so a basic principle, if you're trying to understand something that's big and complicated, is to break it down into much simpler constituent pieces and then try and build your understanding up from that. So for example, if you're a chemist and you're trying to understand big, complicated molecules, you can look at the atoms that make up the molecule and then ask questions about what atoms are there in the molecule, how these atoms are connected to one another, maybe the shape in which they're connected. And this is a very powerful way of trying to get some general understanding of molecules based on much simpler building blocks of the atoms. And similarly, if you're a geneticist, maybe in principle you care about genetic phenotypes. You care about whether some people get certain diseases or have certain hair colors. But this is a very complicated thing. But you can get a huge amount of understanding from looking at how this is influenced by genes, in particular base pairs, and different alleles within the gene, and how these are then inherited from one generation to another generation. And each time we're taking a big complicated thing and we're getting a good partial understanding by looking at the constituent blocks. And so mathematicians are no different. And if you're a number theorist like me, you're really interested in the whole numbers. And back in elementary school, there's maybe two things that you can do with whole numbers. You can either add them together, or you can multiply them together. And it turns out that if you have a very additive problem, often this can be broken down into questions about just the number 1, because every number can be made up from just keep on repeatedly adding 1. But that doesn't quite work with multiplication, and it turns out for multiplication, the building blocks are prime numbers. So the formal definition is a prime number, which is a whole number bigger than 1 that can't be written as two smaller whole numbers multiplied together. So 15 is not a prime number because it's 3 times 5, but 7 is a prime number because you can only write it as 7 times 1 if you're writing it as two whole numbers multiplied together, and they're not both smaller than 7. But if you see this, the natural question is, why on earth should you care about prime numbers? This looks like some esoteric thing that maybe math geeks would like, but wouldn't have any relevance to the wider world. And the reason that they're fundamentally the building blocks is that it's got this fancy name, the fundamental theorem of arithmetic, and it goes all the way back to the ancient Greeks, that every whole number can be written uniquely as a product of primes. And the reason that this is useful is that it means that there's lots of complicated questions about whole numbers that exist in mathematics, but also in the real world, and you might hope that if it's a multiplicative question, you can then reduce it down to a simpler question about prime numbers, and that's a way that you could solve the overall problem. And so I sometimes like to imagine whole numbers as being like molecules and their constituent atoms as being the prime numbers. There's this quote from Kronecker, a famous mathematician, God made the whole numbers and everything else is the work of man, sort of talking about how these are somehow the natural objects for mathematicians to study. So now I'd like to give two examples as to why this role as building blocks turns out to be of fundamental importance, one in the real world that we live in, and one in the realm of pure mathematics. So for example, in the real world, every day now we're using the internet, and I might try and buy something on Amazon. Maybe I'm trying to buy a math book or something, because that's the sort of thing that I buy. But when I'm buying my math book, I'm putting in my credit card details, and I want to make sure my credit card details are secure, so a hacker can't steal my credit card details and use my credit card details to buy himself lots of math books. And so to avoid this, we use a cryptographic scheme where we take my credit card details and we encrypt them by turning it into some other number. And it turns out that in one of the most common and most widely used cryptographic systems, the whole manipulations are to do with multiplying numbers together. And so because it's a problem about multiplying numbers, you can study it using prime numbers. And so from the hacker's point of view, it turns out that you can break this cryptographic scheme if you can turn a big whole number into its constituent prime numbers multiplied together. So if the number that was chosen was 15, it's not too difficult to write it as 3 times 5. But when we take really big numbers, we believe it's very difficult computationally to turn it into its numbers multiplied together. So for example, this is a number that's a little bit bigger than 15, and this was a famous challenge problem. I think, unfortunately, the challenge has ended now, but you used to get $75,000 if you could take this big number and just write it as two smaller whole numbers multiplied together. So I would say, if you're bored in the back of the audience, you could try and work it out. But unfortunately, now I think the $75,000 prize has expired. But the point is, even with the world's biggest supercomputers, we think it would take a huge amount of time. It'll cost much more than $75,000 in energy, as well as months and months and months, if not years and years and years, or decades and decades and decades, to try and turn this into its constituent prime factors. But you can analyze this a little bit more. When is it easy to turn a number into its prime factors? When can you hack things, and when can you not? And it turns out that essentially you can turn a number into its prime factors, and so you could hack the cryptographic scheme if you had a special property of primes that one of the prime factors when you took away 1, itself only had small prime factors. So this is using more ideas about prime numbers being the building blocks to analyze things a little bit further. And so because there's this possible vulnerability that we think in general it's difficult to turn a number into its factors, but there's this vulnerability of one of the factors had this strange property of having lots of small prime factors, various people, when they're designing cryptographic schemes, used what are known as safe primes, which are trying to avoid this property as much as possible. And so they said, if you want to encode credit card details, find a prime p such that p minus 1 over 2 is prime, and then you avoid this issue that Pollard found. So this is an option in lots of the currently used OpenSSL cryptographic schemes, even though it's not actually recommended. And one reason that it's not really recommended is that it's actually a famous 100-year-old open problem about how many primes are there such that p minus 1 over 2 is prime. This would be a really bad idea for trying to encode your credit card details if there were no such primes, because then your computer would just get stuck and you'd never be able to put in your credit card details and make a purchase. It would maybe be even worse if there was just a list of 10 such primes, because then your computer would use one of those primes, but any hacker could also find the list of 10 primes, try each one in turn, and then they'll be able to hack all your credit card details. So this is an example of something that we do, maybe not quite on a day-to-day basis, but we make purchases and we use internet security all the time. It's absolutely vital for our digital economy. And we can start understanding it from the point of view of potential hacking using prime numbers. And we quite quickly start running into some of these questions that are just basic questions in pure math about how many primes are there with certain properties that end up being famous 100-year-old open problems that we don't know how to solve. And there's trillions and trillions of dollars resting on some of these things. OK, so that's one example in the real world. I'd now like to switch gears completely and move to the world of pure mathematics. And so maybe the most famous equation in the whole of pure mathematics is Fermat's last theorem. So Pierre de Fermat, who's the guy on the left here, he made this claim that there are no solutions to the equation a whole number a multiplied by itself n times plus a whole number b multiplied by itself n times is equal to a whole number c multiplied by itself n times when n is some fixed whole number bigger than 2. Apart from the obvious ones where one of the numbers is equal to 0. And this was then very famously solved by one of my colleagues at Oxford, Andrew Wiles. So he showed that Fermat's was true in his claim that there's none of these solutions. And maybe the very first step in Andrew Wiles's proof is to realize that this is a question to do with whole numbers being multiplied together, and you can start using properties of prime numbers as building blocks to reduce it down to the case when n is a prime number. And it turns out for much more technical reasons, this makes the problem much more tractable for lots of mathematical techniques. So I don't have quite enough space on the slide here to give a full proof of Fermat's last theorem. But even before Andrew Wiles's work, which is a pinnacle of advanced techniques in modern mathematics, there was important partial progress beforehand. And in particular, Sophie Germain proved a fantastic theorem, which is a little bit technical, but essentially she proved that if p is a prime number with a slightly strange property that when you multiply by 2 and add 1, you get another prime number, then essentially Fermat's last theorem is true when n equals p. So we only have to prove it for prime values of n, and if n had the property that when you multiply by 2 and add 1, you also get a prime number, then actually, essentially, Fermat's last theorem is true for that value of n. And based on this, it allowed her to prove lots of different cases of Fermat's last theorem. But a natural question when you see her work is, OK, so how many cases of Fermat's last theorem does her work really apply to? So another way of stating this is how many primes are there such that when you multiply by 2 and add 1, you get a prime number. And if you think about it for a moment, this is exactly the same problem that I put up as the question that I put up for the real-world example about how many primes p are there that when you take away 1 and divide by 2, you get another prime number. And so here we have one example which is to do with the security of buying things on Amazon, and we have another example that's to do with work on the most famous theorem in pure mathematics, and both of them involve whole numbers being multiplied together. So both of them can be reduced to relevant questions about prime numbers and patterns in the primes. And for both of them, it turns out that a very relevant question is this famous unsolved 100-year-old problem about how many primes are there such that 2p plus 1 is a prime number. And so even though Andrew Wiles proved Fermat's last theorem, he didn't answer this question. And this is still a very wide open problem. And it's this sort of unity and ubiquity of prime numbers that crops up in all kinds of different places, which is why they're so fundamental and why they're these building blocks. But very quickly, we run into these mysterious questions that the ancient Greeks might have studied that problem of primes p such that 2p plus 1 is a prime number, and it still eludes all the best minds even today. But this motivates trying to understand the distribution of primes as a sort of general abstract mathematical theory, which could then apply to all of these different situations when we reduce questions down to questions about prime numbers. So we've seen the question of how many primes p are there with p minus 1 over 2 prime. A related question to do with cryptography is how many primes p are there with p minus 1 only having small prime factors. It turns out that we know a little bit about that question, and that's quite rare, which is why we don't actually worry too much about this possible cryptographic hack approach of Pollard. And these are just very basic questions in the distribution of primes. So for example, other basic questions that are very famous about the distribution of primes are things like the Riemann hypothesis that was mentioned in the introduction. It's got a $1 million reward. It's sometimes dubbed the most famous open problem and the most important open problem in the whole of mathematics, which is just asking for a very precise answer to the question, if you give me some very large number x, I have to tell you roughly how many primes are there which are less than or equal to x. It's almost the simplest question you could possibly ask about primes, but it's also essentially connected to the most important open problem in mathematics. And another very famous open problem related to the ones that I mentioned before is how close together can prime numbers be. This is one of the most basic questions you can ask about any sequence. And in particular, you can't have two consecutive numbers being prime infinitely often because with two consecutive numbers, one of them has to be a multiple of 2. So 2 and 3 are the only pair of consecutive numbers that are both prime. But we could have them having a distance 2 apart infinitely often. And so the twin prime conjecture is the claim that there are infinitely many primes that differ by exactly 2. And all of these are basically famous open problems that mathematicians have studied for over 100 years, and some of the best mathematicians in history have worked on, but remain open today, and we don't know how to solve them. But the final thing that I'd like to end on is, despite the fact that primes have this fundamental importance and they remain mysterious, we're nevertheless making progress. So for example, work that I've been involved in that was part of why I was awarded the Fields Medal is showing that there do exist very small gaps between primes. So we can't prove the twin prime conjecture that there's infinitely many pairs of primes that differ by at most 2, but we can show that there's pairs of primes that differ by at most 246. And moreover, we can show that there's clumps of primes that come unusually close together. And this is important theoretical progress on some of these big, famous 100-year-old problems, building on lots of work of other people. And similarly, I can't prove that there's infinitely many primes such that p minus 1 divided by 2 is also a prime number, but I can show you a weak version of this, and I can show that there's fixed numbers a1 and a2, such that if you take away a1 and then divide by a2, you get a prime number infinitely often. And so this is a weak version of that question that lies at the heart of cryptographic schemes and that came up in thinking about Fermat's last theorem and the work of Sophie Germain. And it's very much in keeping with all the heuristics that we believe to be true. So maybe you can rest a little bit easier at night thinking that your credit card details aren't going to be hacked. And finally, as was mentioned, just a couple of years ago in joint work, I was involved in making progress towards the Riemann hypothesis. There was a more technical problem that we've been stuck on for 80 years that had been very frustrating for us as number theorists, and we managed to overcome that barrier. And so even though some of these problems are very famous problems that have been open for over 100 years, potentially going all the way back to the ancient Greeks, we are nevertheless making incremental progress towards them. And so it feels like it's a very positive time for mathematics and number theory. And with a bit more perseverance, hopefully we'll start to get big consequences for the distribution of primes and making progress on this overall scheme of trying to understand whole numbers multiplied together by breaking it down into questions about primes and then understanding the primes themselves. So thanks a lot for listening.
All right, I have to say that was my favorite math lecture I've ever attended, so thank you very much for that. Does anybody else agree? Yes, there we go. So I want to encourage you to use Slido. We've got a QR code up there. I'll be monitoring it on my iPad. I want you to submit any of your questions, and we're going to go ahead and get started with a couple here. So first things first, I want to know about what intrigues you. Like how do you go after a problem, and how do you actually approach it? Like what is your process like when you have a problem that you want to go after?
Yeah, so I'm really motivated by these big famous problems. That's what always really drives me. But nobody sits down and says, OK, today I'm going to prove the Riemann hypothesis. So the day-to-day reality is much less glamorous in a way, that you're learning all the literature, all the ways that other people have thought about the problem. And often you're trying to isolate specific difficulties of the problem. And I always like to I always have this motto that if there's a hard problem that I can't solve, then there's also an easier problem that I can't solve, that's somehow an in-between stepping stone. And so I always like to come up with model stepping stone problems that have some of the difficulties in common with the big problem, but maybe ignoring some of the other difficulties. And so I can isolate things and really home in on just one specific thing. And that's a big way that I find helpful to get started.
And do you work alone, or do you bring people into that process?
It's a big mixture for me that I think maybe a majority of my works are now collaborative with lots of co-authors. I have amazing colleagues and co-authors scattered across the globe, but still a number of projects I work on my own. So for me, I think it's a good balance to have some things that I'm thinking about in isolation and some things where I'm bouncing ideas off colleagues.
You mentioned some of these big problems, so I'm curious, what is an open problem in number theory right now that feels most tantalizingly just out of reach?
One is a sort of slightly technical problem, but it's called the logarithmic Chowler conjecture, and it's very closely related to the twin prime conjecture. And so it was posed by a mathematician called Chowler as a way of getting an intermediate stepping stone problem towards problems like the twin prime conjecture. And there's been a tremendous amount of progress on lots of ideas connected to this Chowler conjecture. And so that feels like maybe we're just one or two good ideas away from solving that Chowler conjecture, which would be really exciting progress.
So break that down to me. 1 or 2 ideas. Is that 5 years, 100 years?
So yeah, it's always a fool's game to try and answer these questions. We've had a number of really good results on this, but you never really know when the next idea is going to come and when you're going to be stuck for ages. So I remember Andrew Wiles once saying that if you're ever asked to guess how long should a problem be open for, well, maybe you should think that if you were uniformly distributed in time, on average, you would be halfway between a problem being solved and being open. And so you should therefore guess that the problem will be solved for the length of time that it's been open for.
Oh my gosh, okay. Let's shift gears. So this question came from a math graduate student, Maddie G. How much do you think the role of talent versus hard work goes into becoming a successful pure mathematician?
Yeah, so it's clearly a big combination of the two. That it's definitely the case that there are some supremely talented people who don't really make it in pure math because I don't want to say they don't work hard, but they somehow don't mesh right with the style of working that you need for research and really kind of dedicating yourself to a long-term project. And so definitely, I think there's one thing that's got nothing to do with talent that's a very important attribute of mathematicians, and you hear lots of the top mathematicians talk about how they're like very tenacious and obsessive about problems, and they really wouldn't have been able to solve the sorts of problems that they did if they didn't have this, those qualities in the way that they go about their work. Equally, clearly talent is a thing, and it's always like tremendously rewarding for me to see like all these supremely young people come through who have got exceptional talents in mathematics, and when I'm giving lectures or training them as graduate students, trying to guide their abilities, and they really come up with all these creative ideas that are just wonderful to see. So I think it's definitely a big combination of the two. You really can't have one without the other and vice versa.
Okay, so what I just heard, that if you're a grad student in math, if you're relentless, you're going to win a Fields Medal then, right? Is that, yeah? Is that how that works? This next question is inspired by Pen King Huang, and it was a little high level, so I asked our chair here to break it down for us a little bit. So there have been mathematical advances proposed that have involved such complexity that only a few experts can realistically understand them. So Appel and Haken's proof, did I say that right, of the four-color conjecture, Hale's proof of the Kepler conjecture, and most recently, Makazuki's approach to the ABC conjecture. Does that make sense to all you? Okay, great. What is your take on what a preprint purporting to solve a long-standing open problem actually becomes a mathematical truth?
Yeah, so there's certainly lots of interesting sort of sociological aspects of what mathematicians count as a proof. It is the case that I think math has a fairly unique ability that we really agree almost all the time on when things are right or not. There's definitely disagreements, but I think it's an amazing property of proofs that there can be one guy who puts out a proof and someone points out a small issue in it, and 90% of the time they'll have a back and forth, and they'll either agree that there's a mistake and both of them will agree that, or they'll agree that there's no mistake and actually it's completely fixable. So it's definitely the exception rather than the rule that there are any sorts of conflicts in maths, which I think is a unique and very special thing about math. Sometimes, yeah, when a new paper comes out, there's lots of ways that I go about kind of thinking it through when I'm trying to assess whether it's correct or not. You know, a paper will come out and I might get very excited about it. But there's often sniff tests, and again, if there's a hard problem that I think is exciting and I don't know how to solve, there's probably intermediate problems which I also don't know how to solve and can act as a proof of principle. So one big thing that I look for when I'm assessing a complicated proof is there a kind of much lower level result that's not the big grand result that they're claiming, but serves as a proof of concept that there's a real new idea here. And because the market of math at the end of the day is about ideas. What we really care about is ideas, and if the ideas are correct, then people who are technically proficient in the field can kind of fill in the details. But normally, at the heart of even the most complicated proofs are one or two really groundbreaking, but also very simple ideas. That there'll be a new way of thinking about something or a new connection to a different field, which is at the heart of the big breakthrough that's happened. And that's really the thing that I'm always looking for. And as soon as you see that, you've got a proof of concept that there's something really big and exciting happening here. And that's when the heart starts pumping. You think, oh yeah, they were really onto something and it's exciting.
So with your own work, when you finished the work that got you this wonderful, amazing award, who did you go to prove that you were right? Who did you ask?
I mean, definitely as a mathematician, you start to, you get quite used to having like false positives and things with yourself, so you become quite strict with yourself, I think. And I feel like nowadays I'm well-trained enough that when I have something, I really know it. And again, it might be that even if I write all the technical details and there's little errors here and there, if I have the big ideas, and I know that the big ideas work, I know that any little errors in my papers will be fixable. So one thing is that I feel when you're accustomed to things, you just feel it in your bones. You just know that this is right. You've got something really meaty and juicy here, and that's what I look for in other papers. So often I'll run something by other colleagues, but the main thing is I'm just kind of critical with myself, and I think, what's the really kind of big idea? And if I can't explain what the big idea is in simple terms, then it probably means I haven't really understood it, and there's more that I need to do to really reassure myself that it's right.
Oh, I love that. You feel it in your bones. Can anybody else relate to that? Yeah. All right, so this is from Zion, a biology staff member. What advice can you give to an 11-year-old boy who loves math and thinks that everything is math?
Everything is math, you're right. Yeah, if you love math, you should just absolutely keep on following your passions. Definitely there's some bits of math that some people find a bit dry and tedious, and there were some bits of math that I found a little bit dry and tedious, but there's so much math that's really cool and exciting. So if you already have the bug for math at 11 years old, that's incredible, and you shouldn't feel restricted in anything. You should read whatever math interests you, and you should totally follow your passions, and the more you see math in everything that you look at, the more you'll get out of it and things. So just keep on going down the route you're going on. You're already on the right track.
That's great advice. What part of math do you find tedious? You said it.
So, yeah, I have a personal kind of hatred of writing up my papers, actually. That, again, you have the kind of big, juicy idea that's the really exciting thing. You feel great about yourself. You know that everything is going to work out. But then you have to fill in you have to dot all the I's and cross all the T's. And that can sometimes be a very painful process. And so I really have to kind of drag myself through the process of writing up, because for me, the whole point is the ideas. And as soon as I've had the ideas, I kind of want to move on to the next thing. And so writing up papers is definitely one of the things that I find a little bit tedious.
I can relate to that, for sure, 100%. Okay, so I'm going to jump to Slido. I want to remind you to submit your questions here. You can also upvote one, so if you see one that you like, you can give it a little vote. I'm going to go to our most upvoted one right now from Anonymous. Does AI help mathematicians working on these big questions, or not really, since it would require human verification that the answer was accurate?
So I would say everything is in flux at the moment. That at the moment, AI doesn't help me too much on a day-to-day thing at all. I'm a bit skeptical that AI is going to do a huge amount for really coming up with the big creative ideas. But I think AI has a huge potential to be a wonderful assistant for mathematicians in the not-too-distant future to help with some of the tedious things like writing papers, like filling in technical details that it's sort of well known to the field that techniques like this will work, but dotting all the I's and crossing all the T's is painful. So even if you have to check anything that AI does, there's a huge potential for it to speed up this somewhat routine but annoying process. There's other things like being able to connect parts of the literature, and having much more sophisticated versions of search that I think will help mathematicians a lot. So I'm definitely very optimistic about the fact that AI can make mathematicians a lot more productive, and it will change the way that we work, but more in the way that email has made mathematicians hugely more productive and has changed the way that mathematicians interact with one another and enabled much more collaboration and the internet than AI itself coming up with big creative new ideas. That feels further away to me.
Well, we tested it earlier. You and I asked ChatGPT how to explain your work to a 5-year-old, and it gave me some mumbo jumbo about Legos and a rainbow, and I think there was something else in there, and he basically just put the phone down, like, that's not, no, don't even. Okay, so this one comes from our math chair here. Is it better when tackling a new... thank you. Okay, sorry. Is it better when tackling a new problem to get into it with a clear mind or to extensively study the existing literature?
Yeah, I actually kind of like to ping pong between the two. Sometimes I think I deliberately don't read the literature too much on a problem because I want to make sure that I'm not kind of getting stuck in a rut that the literature has gone on. So I don't want, if I'm going to make creative progress, I don't want to think in the way that everyone else has thought before. At the same time, if I go it completely alone, I'm almost certainly dooming myself to failure. So I kind of need a bit of both. And it's the same when I'm trying to understand a paper. I often try and skim read it and guess what the big idea is. And once I've got the big idea, I try and fill in the details myself. And I normally won't succeed. I'll get stuck somewhere. So then I go back to the paper and I have a look at what they've done. And there'll be another little technical idea that I missed. Then I think, OK. And then I go back and try and fill in the details myself. And that way I build up an understanding of it. And I often do the same with problems that I want to bounce in between the two. So I'll have a bit of a think about things. I'll try some things out for myself. I'll either get stuck or I feel like I make a little bit of progress and I get stuck, and then I go to the literature and see what other people have thought of beforehand. And 90% of the time, they'll have thought of everything that I've done and done much better at it because they've had way more time to think about it. But occasionally, I'll have come up with an idea that doesn't seem to be so much in the literature. And then, that on its own is normally not enough, but then I can maybe combine it with some ideas in the literature. And so I really like to bounce between the two.
And when you're building presentations, do you use Amazon specifically because of Amazon Prime? I don't know who submitted that, but great. I love that. Thank you.
I hadn't even thought of that, but that's so good.
Nice. Okay, so are you concerned that some properties of primes will be beyond proof, the ability due to the incompleteness theorem?
So yeah, I guess I have a belief that most of the kind of really fundamental basic questions of primes, like the Riemann hypothesis, like the twin prime conjecture, the sort of questions I put up there are fully provable using the most basic things. And so certainly in my day-to-day math, I don't really worry about the limitations of axioms and things like that. Most of the problems, if there is, most of the things that I work on, it's saying, are there infinitely many primes in this set? And normally the answer is the obvious one. And so if the result's false, there's normally a fairly kind of computationally easy way of proving it to be false. So if the Riemann hypothesis is false, you can prove it just using finite calculation on the computer, which means that there's the bizarre situation that if the Riemann hypothesis was unprovable, it would be true, just not provably true, which is takes a little while to get your head around. But for all of my day-to-day things, I feel that the most fundamental questions on primes are all within normal mathematics. I'm sure there's more exotic questions about primes where suddenly it's less clear that they're really provable in the way that one might hope. But yeah, for the day-to-day things, I think it's fine.
Do you ever feel limited due to the notation or the inability to communicate mathematically?
So inability to communicate is a huge barrier I find to talking to colleagues in other fields. There's lots of examples of mathematicians in one field developing a nice theory, and independently mathematicians in another field developing a nice theory, and then many, many years later down the line, they realized that basically the theories are more or less the same, but they had completely different notation, and nobody realized that the other was doing the same thing. So I definitely find that math gets super specialized, and it's a very unfortunate barrier that maybe AI can help with a little bit for just kind of trying to recognize connections between fields and trying to communicate with colleagues in other fields. In terms of notation within my own work, it's a sort of interesting, slightly philosophical question because I personally don't feel limited at all, but there's been several times in math that we realized that somehow the notation was maybe holding mathematicians back slightly, and when they had a more general way of writing things, it naturally led to the development of all kinds of new math. So it's very difficult for me to appreciate, maybe I'm too low-minded, to think about what a different possible alternative notation would be and how that would open up possibilities. But the ancient Greeks often didn't think of prime numbers as numbers. All numbers were really like lengths of rulers and things like that. And without the more modern algebraic notation and things like that, it just meant that there were some natural questions that they couldn't really comprehend because it wasn't natural to phrase it in the language of lengths and shapes and things like that.
I think you're a great maths communicator. I just want to put that out there. You are very funny, and I appreciate that to make math like interesting, exciting, accessible. So thank you very much. One question from our audience is, can you talk about the link between primes and complex numbers?
At first sight, I would say that these are two kind of fairly separate areas of study. So complex numbers tend to live in the world of analysis, and particularly with complex numbers, there's like fun links between analysis and geometry over the complex numbers, whereas prime numbers are very much in the world of number theory. But there's also this sort of unity of mathematics, and even when you think things are somewhat separated from one another, it turns out that they linked to one another in kind of completely unexpected ways. So yeah, I work in analytic number theory, and that's all about using techniques from analysis and things like complex analysis that use the complex numbers to study the primes. And none of these connections, I think, are obvious, but the Riemann zeta function, which is one of the core objects and very much at the heart of the Riemann hypothesis, is precisely one of these links where it connects prime numbers to complex numbers, and that provides one link, at least, between these two, at first sight, totally separate fields.
Let's dive more into primes. How many prime numbers do you know?
How long have you got?
I have 20 minutes, no, 11 minutes. Can you tell me what your favorite prime number is?
2's my favorite prime number. Yeah, 2 somehow a very unique prime number. So there's all these theorems that work for all primes apart from 2. And so I think all number theorists would agree that 2 is the most unique prime number. I think they'll probably be split 50-50, whether they hate it the most or they really like it the most.
Looking at the audience, do we have any favorite prime numbers out there? Anybody? What, 17? 13?
13?
13?
13's a good one.
Is that a good one? Do we have any other favorites?
So John Conway said 91 was his favorite prime. He said it's the smallest number that clearly is a prime number, but isn't actually when you go to compute it.
Oh.
Yeah, so 91 is the one number that you need to remember in your head out of all 2-digit numbers that looks like a prime number but is not a prime number.
That's a good one to know. I like it. Let's shift to one of our younger listeners in the audience. I'm in 6th grade and want to publish a mathematical paper. Yes, you do. Go do it. Do you know a place where someone my age could publish? From Ionish, I think.
There are various student journals and things. This is something that I definitely talk to your teachers or mentors about, because different publication venues have very different sort of expectations of what they're looking for in papers. And so this is a super great thing that you're interested in, and you should totally follow it up. Off the top of my head, I can't name the most appropriate student journal, but there's lots of different student journals, and they're for sure things that will cater for someone who's in 5th grade, was it?
6th grade.
6th grade, oh, my mistake.
Yes, big deal. That's middle school for us, so it's a big distinction,
yeah.
Okay, so let's switch now to a graduate student that asked, working with existing open problems is great, but how do I come up with a new problem and ensure that it is good enough to devote a lot of time to?
So for sure this is a art rather than a science in coming up with good problems, and I still question myself whether I've really got the hang of this, that I may be very happy with the results that I've proven, but there's always this kind of question as to, what am I going to prove next? Am I going to try things that are too difficult? Am I going to try things that are too easy but not interesting enough? So I think one thing is to acknowledge that it's not an easy process at all. But my process is normally that I start with a big open problem that I find really motivating, and then I do this ping-pong process of thinking about it, but also learning the literature. And when I'm learning the literature, I'm trying to think critically and think about what are the limitations of the literature, but when could I possibly push the literature forwards? And I find this is a pretty good way of working, because it means that it's always connected in an indirect way, maybe, to a big open problem that I find motivating. So it keeps me motivating, even if my day-to-day thinking is on a much more low-level technical details. But also if I'm sort of thinking about what other people have done and how can I improve what they've done and how can I modify their techniques, it's a sort of guarantee that it's going to be interesting to at least one or two people, because you're building on the work that's already been there and people have already thought about, and you're coming up with new ideas that are pushing forwards ideas of other people. And you have to remember that math is a big collective activity, but if you're doing that, then you're kind of, you have a bit of a safety net that at least those people should be interested in your new ideas.
So just moving the needle, right?
Yeah.
Just pushing it forward. I love it. All right, so now we're going to go all the way to the other side. So is there a place for older mathematicians? So both the Fields Medal and the G.H. Hardy seem to suggest it's a young person's game.
Yeah, for sure, I think all kinds of people can contribute to math. So I maybe mentioned on my slides about prime numbers coming close together. There was this big breakthrough in 2013 that predated any of my work on this by Yiteng Zhang. And he was basically, he had a math PhD, but then he didn't get a sort of normal math professorship, and so he had a teaching position at the University of New Hampshire, but he wasn't really known to the field at all, and he had like one or two nice results, but he hadn't published much at all. And then suddenly he had this huge breakthrough on prime numbers that completely shocked the world, and I can't remember his precise age, but he was age 59 or 60 or something like that. He was certainly a complete counterexample to math being a young man's game in the sense of Hardy. So you can certainly look at correlations and things, but I think there's also lots of examples of people who are much older making really fundamental contributions. Marina Ratner also proved absolutely fantastic theorems that are some of the highest profile theorems of maybe 20th century mathematics, and she proved them well into her 50s. So I think there's lots of counterexamples to this, and so there's definitely a place for older mathematicians too.
Okay, so if you're over 40, don't give up. Is that what you're saying?
Don't give up.
Okay,
yeah.
Okay, perfect. So I love the way you're talking about math. You are so animated, you're so excited about it. I'm completely drawn, and I just want to eat up everything you're saying. So the question is, has your passion always been mathematics? What drove you into this field as opposed to others?
Yeah, so I've never had a grand vision of where my career or anything's going to go. So to me, it wasn't clear. I think when I was a kid, I had no idea that being a mathematician was even a job that people did these days. But at each stage, I think I've always had a bit of a passion for math. And so even if I didn't know that I wanted to do math, first of all, I kind of liked the sciences, and so I'd specialize more in that. And then, I had to choose what sciences I liked, and it was more of those sort of physics, math type courses. And then, what do I want to study at uni? Well, yeah, I think I'll specialize in math then. So at each stage, I've clearly moved towards math. So I think maybe to my parents or to an outside observer, it was clear that I was always moving in a math direction. I remember when I was in middle school, maybe it was even elementary school, I used to play the violin. Not well at all, very, very badly, but there was one year when my violin lessons were after the math lessons. And those years I was particularly bad at playing the violin because the violin teacher just said I was completely distracted the entire time, because clearly I was just thinking about all the maths from the math lessons that had been before, and I kind of couldn't concentrate on the violin at all. So I was, they said, why is James taking these massive steps back? And then they sort of talked to my parents a bit, and they realized that it was because it was after the math classes. So yeah, I think I've always had a bit of a passion for math.
You also shared earlier that you love photography. Do you see the math in photography as well, or is that just a creative outlet for you?
Yeah, it's a bit of both. One thing that I like in math is sort of trying to tease out structure from kind of complicated objects. And I think that sort of idea is like very important in photography, that a standard picture has like too much junk in it, and so it doesn't really speak to people. But really good photographs, they kind of put a very strong emphasis on a few simple aspects, and there's a certain amount of harmony and disharmony in the photograph that's somehow perfectly balanced to really make photographs that speak to people. And so on the one hand, this is a very purely artistic, creative thing, but it's also something that I think mirrors a lot of what I look for in my math research.
I love that. Do we have anybody else here who likes photography? One person. Okay, two. We'll work on that. Oh, we got one, our photographer. Okay, phew. I was like, you got to be able to connect with anybody. All right, so I want to throw some really quick mathy type questions at you here. Do you think an odd perfect number exists?
No.
Why?
I can't tell you why. I guess we've tested everything. Most of these questions in number theory, either there's a very good, obvious reason for it to happen, or it should never happen. And somehow there's too many constraints for an odd perfect number to exist. So I think everyone believes that they shouldn't exist, but we just don't know.
I want you to look at this next question. Is that a real theme before I read that out? Is that really a math term?
That is a math term,
Okay.
yeah.
Can you speak to your contributions to sexy primes? What does that mean?
So
What did I just
sexy
say?
primes are two primes that differ by exactly 6. So they're like twin primes where they differ by exactly 2, but instead they differ by exactly 6. So again, it's conjectured that there should be infinitely many sexy primes. Again, this is a famous 100-year-old problem that we don't know how to solve. But again, like results that I've been involved in with co-authors and other things allow you to prove weak versions of this. So maybe I can't prove that there's infinitely many pairs of primes that differ by exactly 6, but I can give you a list of a few different multiples of 6, and I can say there's infinitely many pairs of primes that differ by one of these multiples of 6.
Okay,
That's
good.
a weak version of the sexy prime conjecture.
I'm so glad that was real. I was like, if I ask that and it's not, it's going to be so embarrassing. Okay. Can you say something about the methods you use in your proofs?
Okay, so it's a little bit technical, most things, but one area of number theory that I work in a lot and I like to think about is sieve methods. And they're called sieve methods because it's sort of thought about for sieving for gold. And in fact, the picture that I had behind when I had my slide on the title, The Distribution of Primes, was some handwritten work I did of performing the sieve of Eratosthenes, which is this old technique going back to the ancient Greeks, going back to Eratosthenes, for finding prime numbers, where you take a grid of numbers and you circle 2, and then you cross out all the multiples of 2, and then you circle the next number that's not been crossed out, which is 3, and you cross out all the multiples of 3, then you circle the next number which is not being crossed out, which is 5, and then you cross out all the multiples of 5, and you keep on going, and you'll end up with circles around all the prime numbers. And the sieve methods that I work on are all kind of inspired by this process. They're much more sort of technically and much harder to describe mathematically, but they're all inspired by this process of the ancient Greeks about finding primes by sort of crossing out multiples of small primes.
And most of your work is on pen and paper, right?
Yeah, when I'm really thinking about things, I'm normally working on pen and paper. I'll do like a few maybe numerical experiments on a computer, but 90% of my thinking time is me just like sketching out little ideas on pen and paper and producing all these scrappy notes and bits of paper that fly everywhere.
What kind of paper do you use?
So it has to be narrow-ruled A4 paper. I'm very particular about that, but then I don't follow any of the rulings at all, and I end up writing all over it in crazy things. So I have no idea why I'm so particular about it, but somehow I am. That's my working process.
I love it. Okay, we're going to go pretty technical here, but I want to honor some of our math grad students. So for a number whole number n, the number of primes less than n was approximately calculated as n divided by log n. Are you guys still with me? Okay, is there any refinement done on this result?
The best results towards this are the best results in the direction of the prime number theorem. And this is essentially determined by the best zero-free region of the Riemann-Zeta function. There hasn't been a lot of progress on this problem, so this is a very notorious problem, and essentially the strongest results go back to Vinogradov and Korobov from about 100 years ago. So we've been stuck for the past 100 years, but if you want to know the strongest results, it's these results of Vinogradov and Korobov that do prove stronger results than the first results mentioned about the prime number theorem.
Okay. Did you get your answer? Yeah, okay, good. So as an outsider, mathematics feels like a combination of disentangled fields. Is there crosstalk between number theory and other fields or recent results?
Yeah, there's a huge amount of interactions between the different fields. I mean, one thing is that number theory in particular it's sometimes said that number theory doesn't have any of its own techniques. And so we always have to be going cap in hand and trying to borrow techniques from other fields. And so that means that I feel in all of my work, I'm really kind of scrabbling around, trying to find techniques from other fields that will help with the objects that are there in front of me. But this means in different areas of number theory, I work in analytic number theory, so often I use lots of ideas coming from analysis and probability and combinatorics, but there's lots of my colleagues who work in algebraic number theory who are using lots of ideas from algebra and geometry, but all of us have to use a little bit of everything, partly because we don't have our own techniques. So I think there's a huge amount of interconnection and crosstalk between mathematics, to the extent that it's very difficult sometimes to really draw these clear barriers between fields, that when you go to a number theory department, there might be me and another number theorist, but it might be that actually that number theorist is much closer and much more able to talk to all the geometers in our department, and maybe I'm much more comfortable talking to the combinatorics guys in the department, even though rather than talk to each other. And so, yeah, I think there's a huge amount of crosstalk, and the distinctions between different fields are slightly artificial.
I see that a lot, at least in our chemistry department here, and I shout out to our dean and our chairs who have done a great job of trying to get us to collaborate. Do you think we could benefit from more collaboration between math and science specifically?
Yeah, I think there's a lot of untapped potential there that I remember, my partner did a PhD in neuroscience. That's when we met, and so I think it was interesting talking through lots of the things that she was thinking about in her neuroscience PhD, because I had no idea about the science, but somehow there were some things where I think I gave some useful insights just because I approached it from a much more mathematical situation, and sort of all my intuition is always to kind of build up a basic model of how things work and to think about what that model would predict or not predict. And so I imagine that should generalize a lot, and I think there's a lot of things that maths can offer to the medical sciences, the biological sciences, the chemical sciences. I think there's already quite well-developed links between math and theoretical physics, at least, and it also goes in the opposite direction, that there's various areas of totally pure math who prove results that are completely inspired by some analogies to physics. And so there's some symmetries that all the physics guys kind of come up with because it's natural for some physical reason that no mathematician would have guessed at all, but then you can kind of see them in your equations, and you can generalize those equations to something that looks like it's got nothing to do with physics at all, but by some sort of analogy, those symmetries are still there, but as a pure mathematician, you wouldn't have guessed that there should be a symmetry here at all, and it's somehow coming from the physics. So I think, there can be helpful things in both directions.
Oh, completely. I mean, they all pop out in each field. Personally, when I first was attracted to chemistry when I was 15, it was because of the math. That's what drew me in. Then I saw explosions and I left your field. But okay, so what currently is the least theoretical application of prime numbers?
The least theoretical. I mean, I feel that buying things on the internet is a pretty concrete, non-theoretical thing to do. So that's probably, that's probably my default answer.
Do you have a stash of Hagaromo in your office?
So Oxford doesn't have blackboards, so we don't really use chalk. But nevertheless, I have a stash of Hagaromo.
Okay, all right. Do you think an odd perfect number exists? We already did that one. Let's see here. We've done a lot of these. Oh my goodness. Okay, how would you recommend exploring or self-studying maths?
So it definitely depends on what you want to get out of it. That if you're a kid who's kind of exploring math because you just think math is cool, then I really think that the best thing to do is to just like freely follow whatever it is that you're interested in. You know, you have a passion already, just like read up on things, you'll hear about cool things that will lead to other questions. Just follow go down the rabbit hole and just find out where it leads. You'll have a great time and you shouldn't worry about things too much. If you're trying to emulate something more like moving towards mathematical research and things, then it's maybe a little bit more important to build up a strong foundational mathematical basis. And so then if you're self-teaching and you want to kind of get a solid understanding of math, it's maybe better to go through some sort of standard textbooks in early courses and make sure you kind of do all the exercises and you really understand what's going on, because that's the thing that there's always a danger of when you're self-studying, that you can maybe kind of read things and kind of understand them, but it's often one of the big advantages of having a lecture or something is that they show you like not only that this is true, but kind of why it's true and how someone would come up with that being true. So it's important to ask yourself those sorts of questions. But for sure, if you're doing it for the first time, I just follow your interests and not worry about it too much.
Specifically the Riemann hypothesis, do you have one resource if somebody wanted to explore it more deeply?
If you want to understand the Riemann hypothesis from a sort of casual interest angle, then I think there's lots of kind of more lay-facing popular science things that sort of talk about the Riemann hypothesis. There's a few different books at different levels. On a very public-facing book is Marcus de Soto's Music of the Primes. That's all connected to the Riemann hypothesis.
That's a good book. That's a really good book.
There's sort of intermediate things Barry Mays and someone else has a kind of book talking about the Riemann hypothesis that's very accessible to someone with a small mathematical background, but it's trying to be a little bit more mathematical about things. If you want to actually sort of study the Riemann hypothesis more seriously, then I think it's very important to have actually a pretty comprehensive background in math, that we have no idea of how to solve the Riemann hypothesis. So you'll maybe be able to understand the statement of the Riemann hypothesis if you go through and you learn complex analysis and you learn number theory and you take a few of those courses either through textbooks or elsewhere, then you'll be able to understand the statement. But if you really want to study it, I think you need a much broader understanding. And so that's the advantage of going through a proper math degree and things that you'll learn in a structured way.
Well, you gave a lot of good suggestions of where to start, though, if you do have the interest. I'm getting the sign, so I have one last question for you. So when you look back at your journey, what's a moment in mathematics that gave you pure joy? Something that made you feel like a kid discovering something for the first time?
I think one of the things, so I still remember when this guy Yiteng Zhang's preprint came out, that this was like clearly a huge result in the field. There'd been kind of gossipy murmurings about this result, but then his paper came out, and the fact that it was his work, not my work, meant there was none of the sort of slight stresses and things about, have I got it all right? Am I going to make a mistake? How are people going to respond? So that was just kind of pure joy that this super cool result had come out, and I just kind of couldn't wait to kind of digest the real ideas that were here, because it was clear that he contributed some like significant new ideas that were going to have other applications and things as well.
Well, thank you so much. Can we please give a huge round of applause for Professor Maynard and giving us his time? All right. That's a long one. All right, I'd like to invite Professor Steve Criselli up here, please.
Wow, so thank you, Kate and James, for a truly engaging discussion. Thank you all for coming here today. So let's give one last final round of applause to James, the 2025 Carrier Medalist and Fields Medalist, James Maynard.